Hello. In this section, I want to introduce two important constructs in Verilog language. One is generate. The other is parameter. So let's first look at generate. Generate is usually used to generate logic with similar function. It will save coding effort. Let's look at the example here. We define an array of 8 bits with 8 elements, then a scale signal with 64 bits. Okay, next we use the generate syntax. It's usually begin with generate and end with end generate. They are always paired. Then in the generate, you can define generate variable using the genvar keyword. Then we write a for loop. That is, it will loop for 8 times. The loop variable using the generate variable. And in the loop body, it's just an assignment statement. That means it will get each element from the array and assign it to some bits of the scale. And there is a name. Okay, this is a block name. For any begin-end coding block, you can give a name after it. This is the block name, code block name. For generate, we usually give a code block name after the for loop. So the function is the same as you write 8. Yes, you write 8 lines of assignment here. So after the 8 line of assignment, the function is get each item in array and assign it to the proper bit location in scale. So this is a relationship. This is an array. Each register represent a 8-bit signal. Then organize them together to make the scale. So as you can see, we write several code here, but actually there is no logic generated by this code. They are just a combination of wires. And please pay attention to that. The unroll of the for loop, here is done at RTL compile time. That is, when you compile the RTL, the compile tool will change. Yes, will change this for loop to 8 lines of assign. They are not unrolled at simulation time. This is a concept you have to understand. So the usage of generate is usually to describe logic with similar function. Yes, you can just write several lines to replace the 8 lines with similar coding. Okay, to use generate, you have to know the keyword generate, and you can define variable using generate var, and unit will be used with for loop. And here, the for loop here will not generate any logic, okay, as they are unzold and the compile time. So there will be no data comparator. Okay, let's see a more useful example of generate. If we want to do the subtract of two 16 by 16 array, each element in the array is 8-bit. How will we code this function? First, we define the two array and the array of result. So if you don't use generate, you have to writing about 256 lines, yes, something like that. You have to write something like this line for 256 times. But with generate, and as this is a two-dimensional array, so we define two generate variable and using for loops. Then in the body, we define the function here. So the effect of this generate is at compile time, and after compile time, the compile tool will replace this generate block with 256 coding block like this part. This part will be copied 256 times by the compile tool. So there will be 256 8-bit subtractor in this silicon. So for each cycle, you can do the subtraction operation for the whole array. Yes, just in one cycle, not in 256 cycles. Okay, this is the first usage of generate. Let's say the second usage. Generate can also be used to generate different logic according to the value of a parameter. Just read the code here. Okay, this is the generate and ungenerate. And in this generate, we use the if-else statement. It will test the value of mode. When mode equal to 1, then it will generate logic with this function. And then cascade with a multiplier. If mode equal to 0, it will generate the function of a subtractor. Cascade with a divider. So according to the value of parameter, the function of this code will be changed. Either under cascade with multiplier or a subtractor cascade with divider. This is done at RTL compile time, not at runtime. So when you synthesize this code, there will only be either a adder and a multiplier or a subtractor with divider, not both. Okay. Okay, this is the two common usage of generate. And how to use parameter, or how to change parameter. How to change the value of parameter, I will talk it in next slide. Okay, in this slide I will talk about parameter. Actually, the parameter defined in a module, you can change it when you instance this module. So look at the code here. We define a parameter d width. Then we use the parameter to define the width of some signals. When I instance this module, I can use this construct to change the parameter inside this module. For example, for this instance, the parameter d width will be changed to live, so it can do the add operation for signal of live bits. The result will be 10 bits. Yeah, line down to 0. And for the other instance, I can give the parameter another value. So this will be an adder of 13 bits. And the result is 14 bits. So use this construct, you can modify the value of parameter defined in a module and module instance time. This construct can also enable the reuse of code. Okay, let's say another example of parameter. This is the module. This is the module of single port HRM model. It has 3 parameters: address bit width, defining the bit width of address; data bit width, defining the bit width of data; and the depth of the memory. That is how many items in this memory. For here is 128. So when we define the input of signal and the memory size, we use these parameters, and we code the memory function here in an always block. This is the write function. This is the read function. So when you want to use this single port HRM model, you can change the parameters. Yes. For example, you can change this parameter to 8 and this to 16. Then you will get a 16-bit wide HRM with depth of 256. You can also change it as then it will become a single port HRM of 64-bit width with 1024 depths. Okay, this is the advantage of parameter. You can parameterize the design at module instance time. And there is a note for you. In Verilog 2004, you can use this system function. Okay, you can use this system function clog2 to calculate the bitwise of a variable. The function of this system call is the mathematical equation for this function call is yes. The return value will make sure the f's power of 2 will bigger or equal to the input variable. Okay, that's all for this section. And the whole chapter is coming to the end. I think you have learned more than 95% of the commonly used Verilog syntax for design and verification. If you occurred some syntax you don't know, you can Google it. And you can use this knowledge to design complex design law. So, in next session, I will give you a coding exercise to check whether you have mastered the coding skill of Verilog or not. This is a problem of complex sequence check. Yeah, a sequence much more complex than the one we have studied in the course. Then in the next chapter, I will introduce some commonly used hardware architectures such as pipeline, arbiter, ping pong, clock domain class, slide window, and pipeline with control, and pipeline with forward pass, something like that. After you have learned these commonly used architectures, I think you have the ability of deal with big functions, such as you may have the ability to design a RISC file, a RISC 5 CPU core, such as a 5-stage pipeline CPU core, maybe with branch prediction, with I-catch, D-catch, with interrupt enabled. Okay, you will have the ability to define such complex designs. So if you are interested in, you can check my homepage on Udemy and find the interesting chapters. Thank you.